Good afternoon, everyone. Thanks for joining us. Welcome back. I'm Steve,
And I'm Scott.
and together we're Backyard Musings, Apple Valley, California.
Yep, the Science and Technology Channel.
Got that. So this is a crazy one. Scott said, and I agree with him. Spiders don't just spin webs; they engineer them. By stretching their silk as they spin, spiders strengthen the fibers at the molecular level, aligning proteins and forming extra bonds that boost durability. Scientists have now cracked this secret using computational simulations and lab experiments, paving the way for bioengineered silk with game changing applications from medical sutures to ultra strong body armor. Would you like to know more?
All right, so when spiders spin their webs, they use their hind legs to pull silk from their spinnerets. This pulling action does more than just release the silk, it strengthens the fibers, making the web more durable. A new study from Northwestern University reveals why stretching plays such a crucial role. Using computer simulations, researchers found that as spider silk stretches, its protein chains align and more molecular bonds form between them. These changes make the fiber significantly stronger and tougher.
Yeah.
So as a
Excuse me.
spider web, so I'm just trying to figure this. As a spider web, because you run into spider webs all the time, right? Or you see them out in the woods
Yeah.
or wherever.
All the time. Yeah.
Yeah, and sometimes they break because insect or something will get in there, and then so the instead of just leaving it like that, the spider comes back and does a maintenance and repair job on it, right? Strengthen it back
I
up after.
guess. Yeah.
Yeah, yeah, cool. All right.
Baba, stop whining. Okay, to confirm these findings, the team conducted lab experiments using engineered spider silk. Their results could help scientists develop advanced silk inspired materials for a variety of uses, from biodegradable surgical sutures to ultra tough body armor.
All right, this is a quote. Researchers already knew that stretching or drawing is necessary for making really strong fibers, said Northwestern's uh, Sinan Keaton, and the study's senior author. Again, to go on with the quote, but no one necessarily knew why. With our computational method, we were able to probe what's happening at the nanoscale to gain insights that can be seen experimentally. We could examine how drawing relates to the silk's mechanical properties. So, okay.
Yeah, that's cool. And so here's another quote. Spiders perform the drawing process naturally, said Northwestern's Jacob Graham, the study's first author. He continues, when they spin silk out of their silk gland, spiders use their hind legs to grab the fiber and pull it out. That stretches the fiber as it's being formed. It makes the fiber very strong and very elastic. We found that you can modify the fiber's mechanical properties simply through modifying the amount of stretching.
An expert in bio-inspired materials, Ketten is the Jerome B. Cohen Professor of Engineering, Professor and Associate Chair of the Mechanical Engineering and Professor of Civil and Environmental Engineering at Northwestern's McCormick School of Engineering. Graham is a PhD student in Kenton's research group. So he obviously
That's
went
cool.
through a lot of engineering classes.
Yeah, yeah.
Yeah.
Researchers have long been interested in spider silk because of its remarkable properties. It's stronger than steel, tougher than kevlar, and stretchy like rubber. But farming spiders for their natural silk is expensive, energy intensive, and difficult. So scientists, I wonder why they don't train. Why don't we get a government study to train silk weaving spiders? Why don't we do that?
I don't know. We got it
I
for
don't know.
everything.
I know. So scientists instead want to recreate silk-like materials in the lab.
All right, back to another quote. Spider silk is the strongest organic fiber, Graham said. It also has the advantage of being biodegradable, so it's an ideal material for medical applications, like you said earlier. It could be used for surgical sutures and adhesive gels for wound closure because it would naturally, harmlessly degrade in the body. Interesting.
Yeah, that's cool.
Yeah.
That there could be battlefield uses for this one. Study co-author Fuzhong Zhang, the Francis F. Aman Professor of Washington University in St. Louis, has been engineering microbes to produce spider silk materials for several years. By extruding engineered spider silk proteins and then stretching them by hand, the team has developed artificial fibers similar to threads from the golden silk orb weaver, a large spider with a spectacularly strong web.
Despite developing this recipe for spider silk, researchers still don't fully understand how the spinning process changes fiber structure and strength. To tackle this open-ended question, Ketton and Graham developed a computational model to simulate the molecular dynamics within Zhang's artificial silk.
Okay. Why didn't they just find a spider whisperer and ask the spiders?
I don't know
what I'm saying.
I couldn't be that because I usually take care of spiders right away. They don't last very long. So
there's no whispering for you. There's destruction, right?
No, it's called the hammer comes down. Yeah.
Through these simulations, the Northwestern team explored how stretching affects the protein's arrangement within the fibers. Specifically, they looked at how stretching changes the order of proteins, the connection of proteins to one another, and the movement of molecules within the fibers.
Ketton and Graham found that stretching caused the proteins to line up, which increased the fiber's overall strength. They also found that stretching increased the number of hydrogen bonds, which act like bridges between the protein chains to make up the fiber. The increase in hydrogen bonds contributes to the fiber's overall strength, toughness, and elasticity, the researchers found. Quote, once a fiber is extruded, its mechanical properties are actually quite weak, Graham said, but when it's stretched up to 6 times its initial length, it becomes very strong. That's so weird.
Normally, that's pulling.
Normally when you think about, like when you bend steel or you disform it, it usually loses its tensile strength, right? Am I using that word right? Tensile strength?
Yeah, well, steel is good in tensile, but not good in compression. When you can compress it flat like a pancake very easily, but you can twist it all day long.
But doesn't it lose some of its strength properties though when you do that? I mean, when you bend
I don't know.
Yeah, I think that's
I don't know. Well, I mean, they do they turn rebar so that they can connect different rebars together. So I mean, they do it in construction.
Right.
All right. To validate the computational findings, the term used spectroscopy techniques to examine how the protein chains stretch and align in real fibers from the WashU team. They also used tensile testing to see how much stretching the fibers could tolerate before breaking. The experimental results agreed with the simulation's predictions.
Quote, if you don't stretch the material, you have these spherical globs of proteins, Graham said. But stretching turns these globs into more of an interconnected network. The protein chains stack on top of one another, and the network becomes more and more interconnected. Bundle proteins have more potential to unravel and extend further before the fiber breaks. But initially, extended proteins make for less extensible fibers and require more force to break. Okay.
Although Graham used to think spiders were just creepy crawlies, he now sees their potential to help solve real problems. He notes that engineered spider silk provides a stronger biodegradable alternative to other synthetic materials, which are mostly petroleum-derived plastics. Quote, I definitely look at spiders in a new light, Graham said. I used to think they were nuisances. Now I see them as a source of fascination.
Well, they need to put them in a sweatshop for spiders because I'm not having them in my house.
Spider exploitation? Scott, come on. We're not going to.
Yeah, that's
for real.
One thing my wife and I have, one of many things that we have in common. We do not like spiders. But doesn't sound like Baba does either. So, yeah.
Yeah, Baba, I don't know. He probably wants a treat. All right, folks. Thanks for joining us. We appreciate it.
Take care, everyone. Have a great day.